Yeah, it's 63. It doesn't increase 63. So it's gonna go. Wait, okay. It's here, and it's okay. So it's so here. Oh, so then what mission? So then 50. Yeah.
All right, guys, so those look familiar? Is that what you guys got, those numbers are? Okay. And then if I do, you don't have to do this, but if I do this, so the sum of L3, well, shit and a half, Jeff, what'd you do? Oh, derp. Smart. All right. Sum of L3, I get 45.89. Yeah? So that's going to be, that's going to be the mean, which looking at the data makes sense. Please, dear God, if your mean is 17, you should know there's an issue, right? There's no way the mean could be below the lowest data point, right? So that kind of thing happens all the time. And this is where students have to stop saying, well, that's what the calculator said. You stop and you say, that can't be right. I probably made a mistake somewhere. I like it. So 45 at least makes sense. It's in the middle of the data. What's kind of true about this data? It's kind of like goes up and down a little bit and then up and then down. So it kind of makes sense the mean should be in the middle somewhere, maybe. All right. And if I do L4, my sum for L4 was 2410.89. I like it. All right, so far so good? And again, I can't say this enough, although some of you guys are like, stop saying it. We have developed formulas based on ideas. The ideas themselves don't change. The look of the formulas will change if I do some math to them. So it's really easy as a student or anybody looking at this stuff to lose touch with what these numbers mean. That is the mean. This, what am I going to do with this? I'll tell you what to do with that, Jeff. No. What am I going to do with this? This is a part that goes where? What do I do with this number? Plug it in. So eventually I'm going to put it where this shows up, which is, of course, right down here. Because now I know what that value is. Let's first do this first question. That might be a good place to start. Let me, you ready? I'm going to tell you this right now. By the way, I sort of didn't, well, all right, I don't make you feel bad, but a lot of people missed the z-score question, so I didn't even try to calculate the percentage who got it right. But we should all know what a z-score tells you. It's going to be the same answer. I could ask you, what does a z-score of 2.07 mean? And then you would say that that data point is 2.07 standard deviations above or away from the mean, right? So that's going to be the same idea each test. On this next test, I'm going to create an x p of x table where the p of x's don't add up to be 1. Is it still okay? Of course it is. They're going to add up to be 0.9999 maybe. Is that really far away from 1? No. We didn't have an issue back when we made histograms and it didn't come out to be 100%, right? And that's really what this is. P of x is just relative frequency. Why could it add up to be something different than 1? Because the numbers they gave me would be rounded, and that's what I'm going to do. Or it's going to add up to be 1.0001 or something. You guys with me? Why do I do that? Number one, to make sure you understand 1 is what it's supposed to add up to be, but as long as it's close, it's okay. And 2, so you don't just write shit by memorization. You actually have to check it. You actually have to do the check. That's what it means by verify. Don't just spew at me what it is. Actually check it. Okay, maybe. So verify this is valid. Well, all the probabilities add up to be, in this case, exactly 1. Yay. And all the probabilities are between 0 and 1. I like it. Yes?
So you still say that? Even though it might be 1.01?
No. So, if there was a problem, let's say the sum of the probabilities on a different problem was 1.00002 or something, right? Don't just say that, because then I'm worried that you don't know what it's supposed to be. You would say, which is approximately 1. So that shows me you checked it, and it shows me you know what it's supposed to be. Bam. That's how any check happens, right? We check your blood, and here's what it is, and here's what it's supposed to be. It want to tell me both to show me the check. Okay, I like it. Now, please, dear God. That's not what happened here, right? But just in case, in the future. Okay. What about this one? What's the probability that some kid thinks they'll retire? There'll be at least 25 when they retire. There's a shortcut way to do that. And remember, I told you that at least 1 was just a specific example of a bigger idea. At least 25 leaves out what? 21. So 1 minus 4%, 96% done. At least 25 is 25 or more. So you could add up all these. But of course they all have to add up to be, from here down, they all have to add up to be 96 because the first one's the missing 4%. So either way you want to do that. I like it. Cool. So I would do 1 minus 0.04, 0.96. Bam! 96% chance. I love the 24% of the kids that would think they retire at 25 thing. They're going to make the next, Instagram or whatever. This one's even better. All right. Yes?
Just to make it a little tricky, what if it says at least 50? So then now you have 2.
Oh, yeah. All right, so if I said at least 50, because you picked up on who I am as a person, I would totally do this. I would just add these 3 together.
And then whatever.
At least 50 would be 50 or more. Because there's no, see how the opposite probability has the exact same amount of work? In fact, more, because then you have to do 1 minus. So it's not useful. That's why the general idea is anytime the opposite probability has less work, do that way. So the opposite for the first one was just 4%. 1 minus that, quick. Right? But here, the opposite has the same amount of work, even more. Because you got to do 1 minus. I like it.
Okay, so now I'm just going to
I really want you to understand that 1 minus thing is just another way to do certain problems. That doesn't mean it's the only way to do them. Yeah. Okay. So what's the mean?
45.
And then this one we identified as having a value of what?
24.
Yeah, 2410.89 minus the mean squared. Right? And what do you get when you do that?
304.9979.
304.9979. Good, that's what I need. Right? And that's the what? Variance. Good, because I haven't taken the square root yet. So then if I take a square root of that, I get 17,464. Does that make sense for the data? The middle was in the 40s, right? So that's about 15 away. That's about 19 away. Yeah, it looked like on average, maybe they got about 17 away from the middle. It makes sense. Do you have to do what I just did? No. But you should have some way to tell if the answer you got looks reasonable. Let me stop there for a minute. Any questions about that so far? Okay. Part D sounds very familiar, but you're going to have to do a different thing to get the answer. First step's the same. Put the mean in the middle. Go down a step. If you go down a step, where do you end up? 28.4, blah, blah, blah. And if you add a standard deviation, you get to 63 point, blah, blah, blah. Okay. So what data points did we just catch? We only caught 40 and 50. Those are the only ones that fit in between those. So we caught all the 40s and we caught all the 50s. If I catch all the 40s, what percentage is that already? 23. So you can't do 40 and 50 as two things out of 6 ages. You can't do that anymore because they're not all weighted the same. So I caught 23% and I caught an additional 18%. So what percentage did I catch? 41%. So that's different than if I just have a listed in. Then you have to do the number that are in there out of the total because they're all weighted the same. Here they're weighted differently. You got to count their weights. Okay, and then finally, there was a piece of information. The very first piece of information I gave you on this sheet was what? It's one of those evil questions I always hate. How far into the woods can you run? Halfway, because then you're running out of the woods. Stupid. What's the very first thing I tell you? Very first thing. Very first piece of information I tell you on the sheet.
1,200 kids.
1,200 kids. Good. So how many kids believe they will retire before age 65? Well, I know how many total kids there were. If I knew the percentage that believe that, I could do the percentage of the total. So what percentage think they'll I was going to say graduate. That's only graduate from work. They'll retire before age 65. Yeah, this is 31%, so 69%. 69% of 1,200 kids, and then whatever the hell that is. 84, so. Who is it? 828. Okay. So 828 kids are really being silly. Because we're already living long. Well, to be honest, the life expectancy has actually gone down a little bit since the recession and all that, but it's still pretty high. We're going to hopefully start going the other way, unless World War III or whatever. Yes.
How did you get 69 again?
Oh, before age 65, right?
Yeah.
Before age 65, which means add these up. Or what I did was that's 31%. 1 minus that is 69%.
And then for the 41, it's the same thing, right? The 41%, the one above.
41%.
On the other problem. The one on top.
Oh, here.
Yeah.
Yeah, we caught the 40s and we caught the 50s. So I just add those together.
Okay.
That's 23% of the data we caught, and then another 18% we caught. I like it. So the idea doesn't change much. It's just going to change a little bit because it's given to us in a different format. Oh my God, I haven't given you a break yet at all. I'm so evil. You guys doing all right? So let's come back at 10 after, and then we'll get back into it. Give you a little bit extra.